this equation, the order of two equations, because here we have F1, and equal H1 times this minus 1.
Yeah,
so it's order of two.
Right. So this example, right, order is 1. So this is 1. In the other example, what is this power have to be? In this example, what is F naught of Z has to be equal to? What is that power? Should be the order, right? Should be 3. And the reason why I have this 3 is to make sure that the system is causal. If I don't care about causality, then I don't care about this delay, right? Because basically this is flipped, right? I have to shift by the maximum order. Otherwise, I don't have causality. In other books, they don't really care about causality, so they don't have this z to the minus. It turns out that this is L, okay? So you can remember that the power of the order here, basically your center of symmetry of P naught. So L goes to here, L is 1, this is 1, so on. Okay, so that is our first factorization, which yields commonality. Okay, let's discuss linear phase. Now, why do we care about commonality of linear phase? It will become clear in the MATLAB exercise. Orthogonality is very good for noise reduction, so forth. If you have white noise, if you have noise, then you would use orthogonality in the application. If you have image and video to process, okay, where phase is very important, then you want to use linear phase solution. So depending on what's the application, you would choose different choices of system to analyze. Okay, so I'm going to discuss now the factorization of P naught into F naught and H naught such that each of them is linear phase. Is this linear phase? Is P naught linear phase? Yeah, look at the uniform response. It's symmetric, right? So tell me how to do it. What do I do with this C inverse system? Can I put C here and C inverse here? Why? Why not? It will not be symmetric, right? Because symmetric means that pair of 0 have to go together. Okay? So if I assign C here, then its inverse have to be in the same Z plane, right? So they have to go together. So that takes care of this pair. How do I distribute 4? 4, 0, minus 1. Okay. What are the choices? 2, 0 here. Okay. 2, 0 there. What are the other choices? Can I erase this? Right? So red color is linear phase, okay? So again, I need C and C inverse, right? One, 3, well, 3, 1, okay? Yeah, so you see that the way to distribute this is 4, 0, pi. You have many different choices, like 2, 2, or 3, 1, or 4, 0. Right? But basically that's what you do. So the important thing is this pair goes together. Is 0 at pi give you linear phase? It's a system with 3 0 at pi. This is linear phase, right? Is that give you linear phase?
No.
Let me erase more and need more. Okay? You can deduct it. Okay? So this is C inverse. That's 2 0 at pi. How do I test to say a system have linear phase or not? If I'm only given the polar plot, I don't want to compute the Z transform and so on and so forth. Too complicated. How do I just look at it and say it is linear phase? Well, you see that this can be factorized into two systems, right? A product of these two systems, right? If FIR system polynomial, I can factorize it this way, it's LTI, right? Do this have linear phase? Yeah. This have linear phase? Yes. Why? No,
because
why the symmetry? I
2 0 is straight.
Okay, so to get symmetry, I have to plot. I have to find the impulse response, right? I don't want to do that. I'm just saying that looking at it, how do you recognize it, right? So this only tells me where the location of the zeros are. So I have to go back to here and check. Here are how the zeros are related, right? So saying that -1 is a 0, -1 is not a 0. So -1 system with 0 at -1 or 1 is always linear phase because -1 is its own inverse, right? And 1 is its own inverse. So any system with 0 at 1 or -1 is always linear phase. And this is linear phase, and this is linear phase. It's a product linear phase. Sure, because phase add. You add to linear, you got linear. Okay, so basically you only have to check to see whether this pair go together or not. You don't really care to check the 0 at -1. It's always give you linear phase system. Is that okay? Okay. So we see that you have two choices, right? The other choice would be 4 0, which is not a good factorization. Okay? And in fact, there are names for these particular choices, okay? Let me give you the name. So this one, if you look at this, the coefficient is 1, 2, 1. I'm ignoring the factor outside here. Okay? I'm just giving you the coefficient of your impulse response. It's 1, 2, 1, right? Because this is 1 plus the inverse square. So it's 1, 2, 1. This one is -1, 2, 6, 2, -1. Okay? This is 1, 1, right? That's 1 plus the inverse. This guy is -1, 1, 8, 8, 1, -1. This choice is called 3-5 system. If you read image compression literature in Wavelets, they refer to a 3-5 system. That's the 3-5 system, which is a system where they have length 3 and length 5 for the field base. Okay, this is the 2-6 system, right? Length 2, length 6.